Hello, everyone. This is Spencer Snolling from Hydromantis, and I'm glad that you've been able to join us today. So today we're going to be talking about advanced sequencing batch reactor configurations and how you set them up and model them in GPS-X. So in this case, when I say advanced sequencing batch reactor or SBR operation, these are specifically a couple examples today we're looking at that allow for continuous filling of the SBR system. So I'm going to go through a couple of examples and show you some slides, and we'll give you an opportunity to learn about how to set those things up. So my name is Spencer Snolling. I'm VP of Product Development here at Hydromantis. And the agenda for today, I'm sorry, I missed my usual comment to remind you that if you have any questions, please type them in the questions box. That's part of the GoToWebinar dashboard that you should be seeing in front of you. If you pop that out, you can type them in. I see that we already have a couple questions. As usual, our plan is that I'll go through my slides and my demonstrations and so on. And then at the end of the presentation, I'll stick around and answer a few questions at the end. So please feel free to ask any questions about today's webinar, or in fact, actually any questions about GPS-X at all. I'd be happy to answer anything that you'd like to know. So the plan for today is that I'll start out by reviewing what SBR model options that we have in GPS-X so that we're set the context for how to use them to model the two different systems that we're going to talk about. So the two examples that we have set up today are the ICEA system, intermittent cycle extended aeration system, and the CAS system, cyclic activated sludge system. That is a way that allows people to have their SBR cycle going on and treatment while still continuing to receive continuous influent flow. So I have quite a few slides where I'll show you sort of all of the options that you need to know, what are the methodologies to set all that up, and different things you're going to have to put in place. And then we have a couple of desktop demonstrations that I'll run, and I'll show you how that can be used. I'm going to touch right at the very end also on one other even more complex configuration. And then, as I mentioned, we'll have time to have a few questions and answers at the end of the webinar. Okay, so starting out with SBR model options in GPS-X. So as you may know, we actually have multiple different SBR unit process objects that can be dragged from the unit process table and put on the drawing board. Now, they all look the same, but they are of different levels of complexity. They all work exactly the same kind of way. It's just about how much flexibility that you require and that you need in your system. So the more flexibility you need, the more options you need, and therefore usually quite a bit more effort to set it up. So we have a very, what we call our simple SBR. It has a fixed order of phases, and you just have to set the duration, and then it knows when I go into aeration mode that I need to go get that airflow rate or DO control set point that you've specified. And then when it moves on to the next one, it knows which particular sections or phases of the cycle should be mixed and which ones shouldn't, and so on. This is what a lot of people use, especially if it's their first time modeling SBRs. It's a good one to tackle with. The advanced SBR is basically the same thing, except you now have a much more flexible order of phases. So you can set the number of phases in your cycle. You can set the order in which you want things to happen, and then also the duration, such like you would in the SBR. So for the simple SBR, you're kind of in a fixed order. It fills and then aerates and mixes, and then it settles, then decants, and then wastes. So with the advanced SBR, you can put that in whatever order you like. I've seen it used in a couple places where people were doing maybe a bit more advanced BNR systems, and they needed to have an anoxic period followed by an aerated period, and then another anoxic period and another aerated period. So you need the advanced SBR to do that. And we won't be dealing with it today, but we also have what we call the manual SBR. And by manual, we mean you have to do everything. And essentially, this is sort of an SBR tank, but without any sequencing code written for it. You need to do that yourself. So that might be where you would implement something based on something other than just simple timing. Okay, so the two that I'm going to talk about today and that we're going to be using as part of our demonstrations are the simple and the advanced. So for simple MBR model operations, it's just known as sequencing batch reactor in the unit process table. It has this fixed order of phases. So we're mixing and filling, aerating and filling if you want. Then we have aerate only, mix only, settling, decant, and desludge. So basically you can have, whatever length of time you need. And you'll see on this menu here, for example, this is a 0 here under mix, meaning we're going to skip right over that part of that particular phase in the cycle. So you don't have to do them all, but they're there for you to use them if you like. In the advanced SBR, you'll see here it's more advanced. You can define what you want each part of those phases, each phase in that cycle to be. So basically, you specify the duration, and now I kind of got a couple of the menus open up here and side by side. And you can see we have 10 phases, and the duration's been set. And you have to specify whether that phase has, whether the tank will be completely mixed during that phase or not. So here we can see at the top, it's 1, meaning yes, it's an aerated phase or a mixed phase. And you can see here that you specify all of the various flows. So this is what it looks like in version 8. We actually condensed several menus together onto one menu format with the newest version of GPS-X. So for example, here in phase 5, that's been defined as the decant phase. And you can see that we have a decant flow setting. It's turned up. We're doing decanting during that phase for half an hour, and all of the other phases is set to 0. So we're not actually pumping anything out at that time. So again, advanced is when you want to be able to have more flexibility and define them as you need them. Okay, a couple other thoughts regarding SBRs with regards to looking at the output and getting out your model results. I'm bringing these up here again, mostly just because I'm going to be showing you a few graphs like this, and I want to make sure that you understand what we're looking at. When you run a regular conventional activated sludge simulation and you run it for 100 days or 10 days or whatever, and you can see some dynamics happening in your system, you tend to get a nice smooth line that goes up and down, and you'll see responses to disturbances in your system. It's hard to see that with an SBR because at all times you've got things turning on and off. So the flow will go from 0 up to some number and then back down to 0 again. And you end up with a graph that looks like this. It's not very helpful other than to sort of see maybe what the maximum number is. So what I recommend for doing SBRs is to actually use the scrolling XY graph type. So what this does is it's basically this same information, but they're only showing you a small window of time. And as the simulation moves forward, it scrolls from right to left. And then you can see a certain window of time moving by, and that is much easier to understand what's going on. There's not all that many uses or particularly helpful times for this scrolling XY graph, but definitely SBRs is one of them. So here you can see if I've selected the output graph type XY scrolling, and I have a scrolling window of 1 day. All the rest of this setting is the same as you would normally have for any graph. We can see actually in this particular case 4 cycles of the SBR. So just to show you what you're looking at here, we can see, for example, this is the decant flow here in blue. This is the filling flow in red. And this is the volume in black. So the volume comes along here during the mix phase, and then we decant. And as the decanting happens, we can see the volume goes down. There's actually a little tiny bump down here, which is actually the wasting, and that goes down. And then when it starts to fill, we can see the volume goes back up again. So you'll see this kind of pattern. I find this to be a very nice and handy way just to visualize what's going on in a given SBR unit so that we can see what's happening, make sure everything's working the way that we want. What you want to see, of course, is that every cycle, it pumps something down and then it fills it back up to the same spot again, because otherwise you'll end up sort of draining your tank or overfilling your tank over time. And lastly, some of my graphs that I'll show later look like this as well. You sort of start out and there's a bit of dynamics and everything as it takes some time to come to equilibrium. This is because, of course, SBRs don't really have what I would call a steady state in the same way that a regular flow-through system would have. And it's because it's a batch. It's because there's something always turning on and off. And what we really want as our answer is, what is the equilibrium of this system after it's been running for a long period of time? And so it's not exactly steady state. You won't see flat lines, but what you'll see is the same pattern over and over again. And so the way to solve that, if you try and use our steady state solver, you'll see that you don't get an answer. What you have to do is run a long dynamic simulation. And by long, we mean 3 or 4 SRTs. So we're showing you can get to, more or less equilibrium here by 20 days. I believe just to make sure it was absolutely at equilibrium. I ran it for 60 days in all of the examples that I'm going to show you later on. Okay, so now there's a whole lot of other stuff that's in the SBR objects themselves. There's lots of details in the menu about how you coordinate and sync up the infilling, influent flow coming in, and so on. And we did an entire webinar on this actually a year ago. So what I'm going to recommend is go to our YouTube page and look up the modeling sequencing batch reactors, the GPS-X webinar from February 2020, and watch that video. We went through it in very much some detail. I borrowed a few of those slides that I showed you here earlier. Anything you want to know about how to set it up is included here. So anything that you need to know about how to sync up the rotation of the cycles and so on will be there. Okay, so now we'll move on to talking about advanced SBR operation. So the regular system, of course, is a batch, which means that the reactor is filled up and then react and then decanted down to get a settling time and then decanted down to get your treated effluent. What this means, though, is that the influent can't really be nicely received in a continuous fashion. So frequently, you'll find that they're operated with two of them in parallel. So while one is reacting, the other one can be receiving the flow or something like that. So, but that is sort of the regular SBR operation. Typically, filling, mixing, aerating. So there's two. So during this time, there's no influent flow coming in. Same thing for the settling. You don't want to have a lot of flow coming in during your settling period because it might disturb and or have, sort of knock your solids up into the system and kind of mix it again at the point where you're trying to do settling. And then, of course, your decanting and desludging phase and then back to filling again. So if you look at this thing, there's really only that one small period of this entire cycle where we're allowed to have some flow coming in. So advanced SBR operations are ones where the system is designed to allow influent flow to be received in a continuous fashion. And that is done in many different ways, but one way to do it is by adding some upstream reactors and then having some flow control and sequencing that allows for those things to be incorporated into the system. So it's kind of like making your SBR plug flow a little bit. You're going to have a reactor in the front which can remain continuously mixed all the time. It can receive the flow, and then some flow from that can be fed as needed into your actual SBR sequencing operation as designed. So there's a couple different ways to do that. The ICS and CAS systems that I'm going to show you today are two good examples and fairly popular examples of that. We get quite a few questions about how to set this up, which is why we wanted to do the webinar on this topic today. Okay, so we'll start with ICS first. And this is a technology by Sanitaire. So, and I borrowed a few pictures of it off the Xylem website. And you can see here very clearly that this is an SBR operation over here, which has aeration in it, and the ability to do decanting through this equipment over here. This level can be pumped up and down as needed. And this is the pre-react zone. So they've put a completely mixed reactor on the front end, and it is hydraulically connected through baffles and underneath here on that wall. So as this system goes through its sequencing, this one is continually receiving flow. Its level will also go up and down, but it will also allow for flow to come underneath and be part of this particular system over here. So this is the thing that we're going to try and set up in GPS-X. So what we're going to do in this case is have two reactors. We're going to have one here that's a completely mixed reactor as our pre-reacting area, and then our main reactor area will be a regular GPS-X SBR object. And then we can go through the phase where we allow influent to come into that first reactor all of the time. And then as that flow is coming in, we will have flow coming into the second reactor at the appropriate part of that schedule. And then we will allow the sequencing reactor to move along as normal. So this is what it looks like when you set it up. And there's more than one way it can be done, but this is a pretty good approximation of it here. So what you'll see, of course, is a regular reactor, and I've used just the regular CSTR here, completely mixed reactor with aeration going on, and we've chosen to do it with a DO controller on and 2 milligrams per liter DO set point. And then the SBR operation is going to be using these settings over here. This is our typical, not quite standard default set of operation, but it is a typical one for this type of a system here. So just so that you're familiar with it, we have the influent flow coming in here. This is the overflow connection point. You don't want to connect anything to this because hopefully if you've got your SBR set up correctly, nothing will ever come out through here. This is the pump that is for decanting your treated sludge off the top, sorry, your treated water off the top of the SBR as the level goes down when you're doing the decanting. So this is the treated system. And then down here is where you are going to be doing the desludging or, you know, the wasting from this particular system as well. Okay, so what this is going to look like when you set it up in GPS-X is using the, now this particular case, we're using the advanced option here. So we have to set up the details about what we want these cycles to do. So this is the advanced SBR menu. Here's the cycle settings. Here's what parts of it are mixed and so on. And then we now have chosen to define these 6 settings or these 6 phases in this way. So now because we set it to be mixed in both of these phases during the aeration and phase, both of these things here, we can make sure that every time that you're saying that something is aerated, that you have this set to 1, meaning we want to model it as if it's a completely mixed reactor. Okay, so this is filling here at the beginning, moving on, doing the decanting and desludging and whatnot. Okay, so now when we move on to the settings in each one of the things for the aeration and for the pumping, we now know that we have those 6 that we've set up previously, and we can set up everything that we need here. So now we're using a DO controller here with a very high DO set point. We wanted to make sure that we were nitrifying in the relatively brief period where we're doing aeration in this system. So that's why we have a lot of air going in there. It's for the purposes of the demonstration today. And on the flow side, when you hit this flow button, it brings up all of the flow settings, the influent flow, the decant flow, and the waste flow. Now, this is where we might differ away from setting up a regular SBR object. First of all, we are going to set all of the influent flow to 0. The reason for this is that we're not actually specifying for the flow to come in at a specific time because it is going to be coming in all of the time. We are not actually going to control that flow coming in. It is going to be dictated to the SBR unit by what's going on in that immediately upstream CSTR. So all of the overflow that's coming from there, or if you've chosen to set it up with a pump and then try to cycle it in for some reason, that would also work too. But in our case, we're just all of the overflow coming in will come into the basin regardless of what we put in here. So there's no need to really, we're not even using these 2 settings here. You'll see that those 2 pump labels are blank up here. So we're not even using that. Really all we're controlling in this case is the decant flow during the 5th phase and the wastage flow during the 6th phase. Okay, so what happens then when you run it forward is that you will be having that cycling of the SBR, you'll have your continuous flow, and some reactions will go on in that CSTR because it's aerobic and it's a regular bioreactor just like anything else we have in GPS-X. And then all of that flow will then come into the SBR and it will operate as required. So here again, I'm showing you this scrolling XY graph with 1 day of window, and we can see we have a schedule of 6 hours. So 24 hours divided by 6 gives us 4 cycles. And we can see here, first of all, in black is the influent flow. It's continuous. It's the same value all the time, all the way through. In red is the decant. So after we've had the filling and reacting, and then we also have the settling phase, then we have our decanting here, which happens for a relatively short period of time. And then our wastage, our desludging happenings here, that's just pops on here for a really small period of time at a low flow rate, and then back into the next phase again. But the filling happens continually the whole time. Now, I mentioned before about running those systems with the regular SY graph. That's kind of a handy way to be able to see how long it took for this thing to come to equilibrium. So this was 10 days. I actually ran the simulation all the way for 60 days just to get it all the way out. to the end and make sure that all the values are sort of had reached their final values. Okay, so this is what the simulation results look like. And I just wanted to show you these just to make sure it's clear what, again, what you're looking at. Now, by default in GPS-X, what we do with the SBR object is we only display a concentration while there is a flow coming out of that particular connection point. So what you'll see is then the concentrations are only shown during the decant phase. So if I'm looking at what is the effluent from the SBR, I'm going to see a bunch of these spikes every so often. And what you'll notice is that, there's a period of time, and usually during the period while the flow is coming out, the concentration is actually changing during that little period of time as we're pumping it down. It's not the same concentration over time because it's still continuing to settle. It's still continuing to react. So you might find that you end up with a little bit lower concentrations at the end of the decanting phase than you do at the beginning of it each time. So you'll note that that's why they have the sort of the pointy shape there, because the concentration continues to change as it would, of course, in reality. So then down here, this is the same thing. So this is showing you total BOD and total COD numbers for the effluent here. And in between, basically it's zero. So this is more or less an aesthetic and a change that we made a number of releases of GPS-X ago in order for people to understand what they were looking at. Previously, we would have had a number up here, but the number would have gone way up and down and fluctuated a lot because, of course, what it was reporting was what is the solids concentration all the time, not just during the decanting phase. So you would see it when it was completely mixed, and it was really hard to pick out what was the actual effluent number. So we've switched to doing it this way. Okay, so then they all combine together, and when you run your simulation, I put it into an outfall here, and you can see the typical numbers you would get for treatment. So this one's doing pretty well. You see our effluent ammonia, our effluent ammonia and our effluent total nitrogen is 12. So we had 25 ammonia coming in. So obviously we're doing a bit of denitrification. There was some anoxic period in that time as well. Okay. So let's see what that looks like while it's running. So I need to find the correct GPS-X layout, which is this one. Okay, so now I didn't want you to have to sit through running for 60 days, so I already did that. And so right here, we can see those effluent graphs that I was talking about earlier. And so if I continue along the simulation here, you'll note that's what a scrolling XY graph looks like. And what we can see from here is that we're getting basically the same thing over and over again. But if we did change the loading to the plant, or we did change the temperature, or any one of these other operating parameters, if I look at these cycle settings, we look at the timing of the cycles and so on, that now gives you an opportunity to go through and see how the effluent is going to change based on trying to optimize these things. So for example, during the period when my colleague Dan and I were putting this together, and I should thank Dan for doing a good job of putting all these examples together for me, we spent a little time actually fine-tuning the effluent solids. We noticed they were a little bit high, so we shaved a little time off of the aeration because otherwise it was nitrifying fine and BOD was fine. And we added that to the phase to allow for more settling so that the effluent solids would be lower. And that's kind of a typical thing you can do with an SBR optimization is say, okay, I have 4 hours or I have 6 hours to work with. Now I know I have to fill for a certain time and I have to aerate for a certain time and I have to settle for a certain time. So what am I going to do during those times? How am I going to divide that up? So you can figure out how to, balance those different things in that way. Okay, so that's what the ICEA system looks like. And if we look at the flow balancing, that's that pumping and desludging and so on happening there. But again, there's your continuous flow, which is what we were trying to achieve with this setup. Okay, moving on back to the slides. Okay, so now let's talk about the CAS system. And the CAS operating cycle is very much like what I was talking about earlier. So you take what I guess you would call a conventional SBR cycle. So same thing as I was showing you earlier, filling and then stop the fill and do mixing and potentially aerating during that time. Then you stop that, let it settle out, and then you waste the sludge and get your treated flow off the top by decanting. So that would be what our typical SBR system would do. So in a CAS system, what you're also doing is putting that another tank up front, such as this, and actually recycling some of the sludge back to this tank. That's how it differs from some of the other SBR operations. So as you're desludging here, or you're sort of wasting and recycling with this one flow here. And what I'm recommending, what we used is a control splitter. It's at the bottom of the flow splitting options in the GPS-X unit process table. So if you're not familiar with this particular way of doing flow splitting, when the flow comes down here, it comes into this splitter, and you set what you want the flow rate to be through this side, and all the rest of the flow goes this way. That's very handy to say, I want to waste a certain amount. So we take all of the flow coming out here, some small amount of it is wasted, and the rest is recycled back into the anoxic pre-react zone. Then this can actually move around and do what it needs to do in the regular setting, and then this can receive a regular and continuous amount of wastewater flow into the anoxic zone and then into the aerated zone. Now, in this particular example, this system, these CAS systems are also, want to be able to receive that flow continuously. And so it has multiple systems in parallel, like a repeat of what I'm showing you on this screen here, in parallel, so that they can be used out of phase with each other. So this, you'll notice, is actually a 4-stage system here. And this is 4 hours. So it looks like this when we put it together. So what this means is that we can fill for 1 hour and then move on to the next one and let that one continue on and do its aerating and settling and so on, where the second one can now have an hour of filling and so on and so on. This allows us to have the ability to always be filling at least one of them because it cycles through them at that point in time when it's ready to receive its next set of flow. So what I'm going to focus on here is how you set this up and then how you get this flow to cycle through to the appropriate parts of the system. So the way we do that is, this is, before I move on here, I'll just mention, this is a conventional 4-way splitter in GPS-X, and all of our splitters actually have this option. Basically, it's called the timer base. Normally, this will say constant, and you can set up most splitters that way. You can say, I want 40% to go this way and 60% to go that way. Or in this case of a 4-way splitter, it was 25, 25, 25, 25. But now if you flip over to timer based, what you're doing is you're saying, I want to rotate through all of the values I'm entering into this menu. I want them to rotate through all of the settings. And what you do is you set it to be 100% 0, 0, 0. Now, in the way that our splitters are set up, as I'm sure you know, you set one option and then we calculate the rest by, we set up all but one of the options and we calculate the last one by subtraction. So 100%, 100%. In the first one, then 0% here, 0% here. Last one we do by calculation, and it is, of course, also 0. So what will happen is that 100% will sort of step its way through each of the 4 spots as we move along, and that's what directs that flow. And you don't need to do anything special. This is a feature that's already built in, and then the last thing you need to do is just tell it how quickly it needs to move on to the next one. So once an hour, we want it to move 100% of the flow to the next connection point. Now, the other thing that we're going to have to do is have it so that all 4 of the SBRs are operating out of phase with each other, so that after 1 hour, the next one in line is ready to receive the influent flow, so that it's at its filling point in its cycle. So we do that with the time shift, cycle time shift parameter in the very bottom of the sheet here. So the first train, we set that up with 0, meaning we want it to start, when you hit start at time equals 0, that's when it's starting its cycle. And then the second train, we put with this option on where it says 1 hour. So what we mean is we want to start its first one 1 hour after the beginning of the simulation, and then 2 hours, and then 3 hours. So what it does is it puts these things 1 hour out of phase with each other, and it all works very nicely. So once you have all that set up, then set them to the usual settings you would do for aeration, such as turning on a DO controller and setting that to 2 milligrams per liter, and using the various settings that are here for the flow. So we set the decant flow and the wastage rate. Now you'll notice this menu looks different. This is because in this case we're using the simple SBR object. We don't have multiple settings for the decant flow for each phase. We only have one decant phase that's already been fixed in place, and we just have to set the flow rate. And you will notice that in this case, we actually are using the influent flow setting, and we've specified that we want it to be using this label here. So what it does is it takes this flow rate and it applies to this pump, and then that starts pumping it in from that upstream tank. Right. So what we've got then is, simulation results that look like this. So just to show you again, if we run for a long 60-day simulation, these numbers kind of settle down after a while. Probably didn't need to run 60 days. I probably could have got away with 30 or 40, but nonetheless, 60 days gets the job done. And then running with, I ran a little bit beyond that now, and you can see this is what it looks like when you run with the moving one-day window. Now, notice this is quite a bit different than what we were seeing before. And the reason here is this has a much different style of filling and decanting. So it's only 4 hours for one thing. And you'll notice here, for example, this is the filling, I believe, and then our react phase and settling phase. And then here is our decanting and our waste flow. Now, this previously was, of course, a very narrow range. We actually were, doing the wasting for a very small period of time. In this case, we're actually doing wasting and recycling sludge back to that anoxic pre-reactor tank. So that's why you might see a little bit longer period for this. And then as soon as that's done, we start back into filling again on the next phase. Okay, so once you run that for a long period of time, this is what it looks like. And now what I'm plotting here is actually the combined effluent of all of the tanks. And you'll see these little bumps every time it switches from one reactor to the other. At the end of a reactor's phase, it's always just a little bit better performance than it is at the beginning because it's had a little longer to get through its phase, more react time, more settling time, and so on. So that's why you get these little bumps exactly every 4 hours when it switches from the one that is now completely at the end of its decant phase to the one that is just beginning its decant phase. Okay, so let's move over to the next one. Here we go. So we can see this system all set up here, and we're using the simple SBR objects here. And so what I'm going to do is go back to this flow balance page, and I'll just continue on that simulation that I was running before. And as I mentioned, you can see here, while we go through the phase, while we're decanting, the volume goes down in green here, and then when they're filling, it goes back up again. And you want to test and make sure when you're setting up your system that you're filling it back up to the same point again. We go through quite a bit of that detail on how to check that, do your proper flow balancing as part of our SBR webinar from last year. Okay, so let's take a look at some effluent here. And as I mentioned, you're seeing the result of what's coming out at this particular connection point here. It's really interesting when you're using this splitter here. So as I mentioned, it's going to go 4 hours to the first one, 4 hours to the second one, so on. You can actually see that really nicely just on this tab right here. So just look here, there's the 1,000. It's going to go to the third one. It's going to go to the fourth one, and back to the first one again. This is a nice way to sort of visualize the flow moving through these, just to make sure that as you go through the process of setting up your model, the flow is actually going where you think it is. So it's a nice way to just double check everything that's happening in your system. All right, so in this case, yeah, we're actually doing extremely well. We're not nitrifying quite as much, but our effluent nitrate is like 3. So we've all that anoxic zone and anoxic time in the reactor as well. We're denitrifying quite a bit, I think. Okay, so let me touch back on the slides here. How am I doing for time? 2:35. Okay. So I will talk just briefly here about another system called Unitank, which we sometimes get questions about as well. So the Unitank system is a little bit, or actually I would say a fair bit more complex in order to put together. So wasn't able to make it part of today's setup, but if you're interested in knowing more about how you would do it, please feel free to email us and we can give you some guidance on that. So this Unitank SBR design from Keppel Seegers is is one where there's actually 3 reactors, and it fills to the middle one, and then the 2 on the outside operate like SBRs out of phase with each other. And so one side can be aerating, such as it's showing here, and you can see lots of mechanical aerators moving here. The middle one seems to always be completely mixed all the time, and then the other one will be doing the opposite of what this one has done. So, and you have overflow from the middle into the other systems. So that way, it requires a fair bit of sequencing and control of these systems to allow them to flip back and forth and to make sure all your flow splitting goes the right way around. And so basically, as this one is finished its react phase, it will go into settling phase, and then the flow that's coming into the middle and then going this way would then flip over and go that way, and then the effluent would be taken from decanting off the other side. So it is quite a bit more to it than what some of the other examples that I've showed you before, but it is an interesting system, and actually I got to model one of these ones in quite a bit of detail very early on in my career. Back in like 2003 or 4, I think it was. So there's a little bit more required than just the usual kind of setup. So in this case, we can put 3 of these reactors together and feed to the middle one, and then also feed to the outside one. And you'll notice here the effluent from the middle tank can then be fed via the splitter either over into this one, or it can be fed through the splitter this way. And as the sequencing happens, it will flip back and forth between those 2 sides. And same thing here, so that the effluent that is coming off of this can be sent the other way around as well. So basically, you need something that's going to control all of these things, splitting the flow to the right way, controlling these splitters back and forth, and then controlling the sequencing operation of all these 3 things. And that can be done with our scheduler object, our process schedule object, in concert with the sequencing that's already built into these 3 objects here to do things like wasting and so on. So this example works pretty well, and there's not exactly one way of designing and operating these things, and so I've seen a couple of different examples. You can see here they even have different shaped tanks as well. So depending on the way your system might be operated and running, we might be some different ways to set it up in the most straightforward way as possible. So what I'll do is I'll say to you, if you have a unit tank example with this sort of concept that you're using, and you want to know how to do it, then get all the details about how it's operating and then tell us, and we'll sort it out for you and tell you how to configure your influence scheduler. Because what this is doing sort of like the same work that a timer would work, or in fact the scheduler code that's inside the SBR unit, where you specify a number of different parameters to control, and you specify out a scheduler for those things, a schedule with a series of phases that then repeats over and over again. Okay, so winding that up, the advanced SBR operation certainly can be achieved through combining different GPS-X objects, most often by doing some other reactor immediately upstream of the SBR object, and then the selective use of flow controllers and flow splitters, and recombining flow back in again, and so on, and then combining that so that it all sequences together in the way that it should. So, and we get a lot of questions about the ICS and CAS systems quite a bit. So those are the most common ones that we have people ask about, and so now you've seen how to specify those things.